In this video, we will continue to examine drag forces and understand some of the physical mechanisms behind drag forces that depend quadratically on the speed of the object. Consider a cube moving through a fluid with a constant speed of v. From the cube's perspective, the cube is stationary and instead the fluid is approaching it with the speed v. What happens? Well, the fluid molecules will approach at speed v and then rebound. We will assume that they will rebound elastically and that since the cube is much more massive than the fluid molecules, that the speed at which they rebound is essentially at speed v. Now, of course, this is an approximation. In reality, it won't be perfectly elastic and the rebound speed will not be v because the cube is not infinitely heavier than the molecule. We use this picture to determine what the impulse on the cube will be. Well, if this is an elastic collision, then the impulse on the cube will be the negative of the impulse on the molecules because they are simply exchanging momentum. So the momentum lost by one part of the system will be gained by the other. We can write the impulse on the cube as the integral of f drag dt, and we can write the impulse on the molecules as delta p, and the minus sign carries over. And so we obtain a rough expression for f drag. The magnitude of f drag will be approximately delta p over delta t, where this side is referring to the molecules. However, there's more than one molecule colliding with the cube in a given amount of time. So delta p is the change in momentum for one collision times the number of collisions in a time delta t. The change in momentum of the molecule for one collision has a magnitude 2 times mass of the molecule times the speed v, and we want to multiply that by the number of molecules met by the cube in a time delta t. We can rewrite that by taking 2v from this term and multiplying the mass of the molecule by the number of molecules met in a time delta t. And so this becomes 2v times the mass of fluid that is swept through in a time delta t. But we know that mass is the same as density times volume, so this would be 2v times the density rho times the volume swept through in a time delta t. But the volume swept through will be the area of the face of the cube times the distance that it travels, which is v delta t. Putting it all together, we find that delta p, the net change in momentum, is 2 times rho times the area of cross-section times v squared times delta t. Since the drag force is delta p over delta t, this gives us that the magnitude of the drag force is approximately 2 rho a v squared. Now, as mentioned before, in this derivation we assumed that all the molecules bounce perfectly elastically, and that's what gave us the factor of 2. In reality, there are some inelastic collisions. Some molecules after rebounding do not rebound exactly in the opposite direction but at an angle, and similarly some are just pushed to the side. And so in practice what we have is f drag quadratic is kappa rho a v squared, with kappa most of the time lying between 0 and 1. For a sphere, we find that kappa is approximately 1/4. And so for a sphere, we have expressions for both the quadratic drag and the linear drag. The quadratic drag is kappa rho a v squared. The linear drag is 6 pi r eta v. The ratio then simplifies to, for the case of the sphere, 1/4 rho pi r squared v squared. Remember, a here is the area of cross-section, not the total surface area, so we just have pi r squared. The denominator stays the same, 6 pi r eta v. Eta, remember, is the coefficient of viscosity. we cancel out some terms and we find that F quad over F linear is rho RV over 24 eta. It's common to, instead of using the radius, use the diameter, so we can multiply the top and bottom by a factor of 2 and get rho times d times v divided by 48 eta. And this combination, rho dv over eta, is denoted by r, and so we have r over 48, where r is the dimensionless Reynolds number. You can see it's dimensionless looking at this side. A force over force cancels out the units, so it's dimensionless. The Reynolds number is quite important in fluid dynamics. More generally, for shapes other than a sphere, we write r is equal to rho lv over eta, and sometimes instead of r we write re to remind us that it's Reynolds. And L here is a typical length scale of the object moving through the fluid. As we can see from this derivation, what the Reynolds number does is it compares the magnitude of the quadratic drag, which is based on so-called inertial effects, that is, what happens by the object simply sweeping through the fluid, with the importance of the linear drag effects, which are based more on viscosity and intermolecular attraction. And so, when r is small, the flow is laminar, because the linear term is dominating. That means the viscosity based term is dominating, so the flow is laminar and viscous forces dominate. And when r is large, the flow is turbulent. You get vortices and eddies and mixing of the fluid, and inertial effects dominate. What is the critical value of r? At what point do we switch over from linear viscous forces dominating to quadratic inertial effects dominating? In other words, what counts as r being small and what counts as r being large? It's not simply comparing it to 1. Unfortunately, the answer is that this is geometry dependent. It depends on the shape that you are investigating. The good news is that it is mostly only geometry dependent. So if you are looking at water flowing in a channel with a rectangular cross section, then it doesn't matter what the size is, only the shape of the channel. Similarly, if you are looking at air flowing over an aeroplane wing, it does not matter what the size of the wing is, only the shape of the wing. What exactly does this mean? It means that if you want to model a full-scale aeroplane wing, you don't have to build a life-size model to investigate it. Instead, you can build a smaller model with the same shape and then investigate it under conditions where the Reynolds number is the same. This is the importance of the Reynolds number and other dimensionless numbers in fluid dynamics. It allows you to model systems of vastly different scales in the same way as long as these dimensionless numbers remain the same. As mentioned before, this is used in the aeronautical industry, where in the exploratory phase they can examine the behavior of a new model of car or aeroplane or submarine by building a scale model and testing it under conditions that have similar Reynolds numbers to their real-life conditions. The same goes for water flowing through a dam, for example. And again, let me emphasize that the critical value of R, where it switches from laminar flow to turbulent flow, is geometry dependent. And what counts as large depends on that geometry. So in some cases, 2300 is the critical value of R. And so for numbers greater than, say, 3000, you would get turbulent flow. For numbers less than 2000, you would get laminar flow. However, in other situations, a Reynolds number can be, the critical Reynolds number can be as small as 5. There is no hard and fast rule, and it is geometry dependent, but once you determine what it is, you can use that same geometry and at different length scales to determine how it behaves. In general, for us, we will say that F quad over F linear drag is CV squared over BV, where B and C are constants that depend on the shape of the object and the fluid that it is moving through. For a sphere, we can further break up c into gamma d squared, we can break up b into beta d, and so this gives us gamma d over beta times v. Since we are often interested in objects moving through air, we present here the values given in the textbook for beta and for gamma. And so putting those together, for a sphere moving through air, we find that the ratio of f quad over f linear is given by 1.6 times 10 to the 3 seconds per meter squared times the diameter d times the speed v. This shows us that unless we are dealing with small velocities and diameters, then most of the time the quadratic drag force will dominate.